thank you for coming today. I'd like to share with you BT's experience of providing some very large networks to some very large customers. The network I'm currently working on is bringing together the networks of two major banks, which is about 2,500 endpoints. In common with most other customers, that bank his IT function is under immense pressure from his business to reduce costs, whilst at the same time increasing functionality, bandwidth and performance. I'm not going to take you through that customer's particular needs, but I'm going to take you through the general case of things that we're interested in. Starting by looking at where we're really going with service requirements, how we design things, to look at specific application requirements of this kind of corporate network. I then want to look at the things that actually affect performance, and finally look at more detail the impact these have on the applications and how we can start to control that through the use of quality of service. Finally, I'd like to look at how we actually measure some of this stuff and report back to the client. Most networks are built upon a common transport infrastructure, upon which is built an MPLS infrastructure amongst other services. That MPLS infrastructure will comprise of a number of virtual private networks which are allocated to different customers. Each customer will have its own or several MPLS virtual private networks and will be managed by an entity that is responsible for the service delivered over that network. In particular, whether it meets the particular set of service requirements defined for that customer. We're interested in a number of things here, not only network performance, but also network availability as well. So what we do is we provide a degree of resilience in the access network to optimize use of the resilience inherent in the MPLS infrastructure. That will typically be by using dual routers and dual access links for the sites that commercially warrant it. But we'll tend to use a cheaper technology at lower value sites to allow for usually an equivalent level of service, but with perhaps less reliability. So when we design these networks, we're really looking for can we support the applications the client wants and the places he wants when he wants them? Is the network responsive enough to meet his needs? And this is where the level of support for applications comes in. Can we guarantee that we meet his requirements for availability? And can we minimize the impact of component failures? This is the use of duplicate routers, duplicate access links, where appropriate, and of course the appropriate use of routing protocols to route around failures. And finally, most importantly, given the cost climate we're in, is the service affordable? So applications tend to be divided really into three parts. This is according to RFC 3729 by Volbusser. Basically, he suggests three types of applications: transaction-orientated, which are the normal web-based applications that most customers will use to interrogate databases, that kind of thing, and also for things like voice. Throughput-orientated, which are very much the standard file transfer, which still make an important point. The issue here is that you're interested in throughput rather than response time, which is a significant difference, as we'll see when we come to consider quality of service. And finally, streaming orientated. Until the last session, I hadn't a great deal of experience of streaming orientated protocols, but certainly in looking at the variable bitrate optimization mechanism for UMTS, that seemed to sum up what was required admirably. You'll see here that what Walbus was trying to do, and this has never, as far as I know, been implemented, is record performance based not only on a mean, minimum, and maximum achievement of those metrics, but also record availability on a per application basis. I've never actually seen this done, and the general practice in the industry is to record performance on the basis of quality of service requested. So, what kind of things drive application performance? The first thing really is the queuing inherent in the network. Generally, the constraint on performance is where the plentiful bandwidth of the LAN meets the more restricted bandwidth of the wide area network. Typically, their data arrives at the WAN interface according to a Poisson distribution and will be onwardly transmitted through the service process using either a deterministic algorithm, in the case of fixed length packets, or a Poisson distribution for variable length packets. That tends to give increases in queuing delay as you get past the 70% utilization mark. This is an issue for most things, except when you come to consider TCP type traffic across a LAN and WAN, as was done in the 90s when they found that the arrival process was not, after all, Markovian, but was was a much more self-similar looking process, whereby rather than being memoryless inter-arrivals, the arrivals between different packets tended to be related. What that does is create much more bursty traffic, and bursty traffic that is replicated across different timescales with a Poisson type process. The traffic peaks tend to be averaged out over time. This is not so with self-similar. The upshot of that is that on this model, we actually find that the more self-similar traffic you get, the bigger the delays. So consequently, the traditional methods of modeling delays do not hold and give an underestimate of the delay. These are average response times. These are not what a customer wants to see in SLAs. Customer is much more interested in things like a 95 percentile guarantee on service levels. This cannot be assessed by the methods I've discussed. What you find is that 50% of your traffic will be within the mean time scale. And on this case, I've taken a mean value of 11 milliseconds. But actually, even to get within 99.85% of packets to live in that time scale, you need to be quoting a target of about 22, 23 milliseconds. So again, taking averages gives you a vastly over-optimistic view of what can be achieved. There are much more rigorous means of evaluating this, largely a theory known as large deviation theory, which specializes in analysis of distributions out in the wings there, will give you a much more accurate value of whether you're likely to be able to reach the 99.85 or better target. In effect, what those techniques do is allow you to evaluate a thing called an effective bandwidth, which is a bandwidth you need to supply in order to let you get within your target. These treatments are highly mathematical and largely not within the means of the normal network provider. So, how can we exercise some control over this range of applications? Quality of service provides a number of means of doing this. This is based on the diff-serve model, which is typically implemented on 6 levels. typically a very high priority one, which minimizes application delay, jitter, and packet loss for voice to give you reliable communication. Assured forwarding 4 tends to be used by video, and video is perhaps the newest application delivered in corporate networks. Perhaps it's been much more common on the internet for a much longer time. AF3 tends to be used for voice signaling, and the remaining traffic seems to be allocated between the lower 3 classes. Particularly, default will be used for general web browsing and file transfer. This table gives an approximate view of the characteristics of this kind of traffic. So the application is on the left. The kind of queuing mechanism, which you'll see will vary, the protocols involved, and the characteristics of those protocols is shown. Thank you. So how does that fit within an overall service level regime? Interestingly enough, network performance is not considered the most important characteristic of the network. If you remember, I told you that a lot of networks have been sold on the basis of reduced costs. Those reduced costs only begin to be realized as you roll out a network infrastructure. Therefore, to guarantee the cost savings that you're talking about, you have to at least deliver your network to time. Otherwise, cost savings are not realized, and either the provider takes the hit for that in the form of service credits, or the customer does. And guess what? The customer rarely does. Those tend to be the biggest penalties that any provider will face. After that, the in-life penalties tend to be handled by availability measurements. And finally, network performance tends to come a significant runner-up, unless there are significant customer complaints. And interestingly, we talked about in the internet case, proving that you could meet specific numerical targets. What we find in the corporate case is it doesn't matter what those numerical targets are. If the customer thinks he's getting a poor service, he has the commercial clout to make sure that you smarten your act up. Availability, again, needs a further concern. In early networks, we used to measure availability across the network on a hub and spoke basis. That was very useful, but was very kind to the service provider because of the statistics. What customers now expect is to have availability measured on a per connection basis, largely because he likes to have a more granular definition of service. So out at his smaller branch sites, he might have a lower availability specified than at his head office branches. One of the classic things, though, is some customers say, actually, I'm not just concerned about the availability I get, but I'm also concerned about downtime. What this graph shows you is downtime measured across a year against specific availability. And when you're at the left-hand end, then basically you have lots of time to fix faults. As you get towards 99.9%, and heaven forfend, the magic 99.95%, you now have minutes to restore service, which classically you're unable to achieve or unlikely to achieve. So how do we measure these things? First of all, as far as availability goes, it's all down to the OSS system. The OSS system, first of all, has to pick up faults and be able to determine root causes very quickly. This is done by trap collection mechanisms and root cause analysis tools. Following that, the duration of faults tend to be recorded in the trouble ticketing system, which may actually be triggered by the OSS, by the trap collection system as well in some cases. Sometimes it's automatic, sometimes operators are asked to confirm. Response times tend to be coordinated using, calculated using pseudo-transactions across the network. In this case, we use packets typical in size for real traffic, but only sent on a sample basis, one per class of service. In reality, the real, everywhere we're interested in delay, but it's really the EF traffic where we're interested in jitter and packet loss more than the others. We, of course, would be interested in packet loss for AF4. Basically, that covers the bulk of my presentation. There is more in the paper. Thank you very much for your time and attention.